So today again we'll wrap up. We already wrap up. Today I will talk about something that I would like you to know. Again, it won't go onto your final. Uh, and we'll talk about linker, object file, and makefile. So when you talk about linker and object file, right? When you compile C code, right? You can imagine some program doesn't only take one C file. You can develop a bigger project with multiple C files. Some of the file would handle certain tasks. The other set of file would handle a different set of tasks, right? So when you compile this together, there's multiple steps, right? These steps involve pre-processing. Pre-processing basically, as the name suggests, right? Put together all the files and make sure I have all the inputs before I start to cook up this binary file, right? Then you would compile. And when you finish compilation, you assemble them together, right? And then you perform the linking process at the end. I love to compare this to cooking, right? So how many of you cook as a hobby, or like how many of you cook before? So for those of you who cook, right, what should be the first step before I start cooking? Yeah, you would prepare the ingredients, right? So that's kind of like the pre-processor steps. Now that you have the ingredients, what do? You put them together, right? That'll be compilation process, and you assemble them, right? Once you start cooking, your ingredient would blend and kind of mix together into the cooked products, right? And then you would plate them, and then when you plate them before you eat it, right? Some dishes requires additional things like condiments or additional like stuff that goes on the plate, right? So the same process apply to when you compile and run the program. You would do the pre-processing. Every single program when you compile, GCC would kind of pre-process your file. Then it would compile the code, right? When you compile the code, you start to assemble the output file. The output file is these are binary. These are binary where your computer can start eating this, right? I can start eating that. I mean, from the computer point of view, right? You would eat the binary file, but sometimes you also can link multiple binary file together to build a meal, right? To build a meal, to build a good meal, it actually consists of multiple dishes. So that's why I would compare to this cooking process, because if you look at the pre-processing steps, right, this is essentially process every single information that you have on your C code. What are these information? This thing can include the header file. The header file that you have been using so far, what's in there? What goes into the .h file? What would be included in a .h file? So functions, right? I mean, to be precise, the declaration of function, yes. So define things, right? Things like the pound define, right? So these are the definition of certain elements of your program. Like these are the new function names that I'm gonna create it. It does take these many inputs. The input types are integer and string, or I mean integer and character, for example, right? Then the pound define would basically map, right? Certain text to another different text. You can also do things like pound symbol, right? Such as if not defined. So let's say you have a big project you work with your friends, right? It include multiple C file, right? So one thing you can do is to check if this symbol has not been defined. If the symbol has not been defined, you can do pound define if that's the case, right? This would allow you to double check, has someone make a definition for this particular term already? If not, I will define it. Then the next step is once you have this the code pre-processed, right? You would then do what we call tokenization, right? What is a token? Token is basically actually I don't know how to define tokens, to be honest, but you know what is a token, right? It's like it can be a coin or things that the item that you can use, right? So tokenization is basically apply a way to transform your text, such as something like, oops, sorry, a oh, pen, a equals b plus c, right? These are texts. The texts include a equals b plus c. What are the operation? The operation is the operation of this. I have b and c as an input, right? And then they are being added, and that results into the variable a. So you can tokenize this into the actual operation, or the actual operation. This is basically transform your text into the actual operations in form of a token, so that you can use this for the compiler. The next step is, now that you have all the token process, you know the operation, the compilation would happen then, right? Tokenization is the first part of the magic. You start to tokenize things into different operations. Then the compiler would put together the second phase of the magic, compile, so that you have the assembly code. It converts tokens into assembly, right? Assembly that you learn, assembly part 1, assembly part 2, and assembly part 3. And hopefully many compiler would also perform optimization. We'll talk about this today as well, on how GCC perform the optimization. And then you basically have the assembly. The assembly, in most cases, these are the .s file. They'll be generated. These are typically done silently and you fed to the assembler, which would give you the binary, but the compilation process give you assembly. Once you have the assembly code, right, the next step is the compiler will comes in and assembler things together. This is kind of like the inverse of assignment 3 part B. In assignment 3 part B, I have binary. I want assembly code out of this. Assembler is an inverse of that. Part B, we call this disassembler. Disassembler is the inverse of assembler. Assembler is if you have assembly code, you then create the binary, the ones and zero. So the conversion is basically, the key idea is to convert the assembly code into binary so that your computer can now start to eat your code to run the program, right? So now that you assemble together, after you finish, you then get the object file, right? So typically every single C code would generate its own object file or the .o file, right? So with this, right, let's say you're working on a huge project with multiple C code in one project, and you want to build one binary, right? One executable file. This process is called linking. Link every object file, link every assembly file, the result of the assembly file together, right? There are times when sometimes you compile multiple files. What's an example of that? How many .c file that you have in assignment 3? Is there one .c file or is it multiple .c file? It's actually many .c file, right? So if you check the Makefile, there's actually multiple steps involved. We'll talk about that particular file at the end of today's lecture. But if you think about it, there are many .c files, and they work together into a program that would perform the task that we ask you to do, right? So when this happened, the compiler and the assembler basically would generate multiple object file. This is like when you want to cook a fancy dinner with multiple plates, right? How many times you have to go to the kitchen to cook the next dish? So let's say you want 5 different things on the kitchen, on the table, right? 5 different dishes. You would cook 5 different things separately so that you have 5 different dishes so that when you go and eat the food, you enjoy eating everything together. Same things here. You could compile each of the C file into its own object file so that the computer can eat this object file as in the binary format and perform whatever task you're telling them to do, right? So when you have this, you can link them together to create one single executable. So let me go over the high level overview with the more like a figure like slide, right? So this is a high level overview. You have multiple file, right? File 1.c, file 2.c, and file 3.c. So what you do is you can compile them together, right? When you compile them, you get each of them a separate .o file, the object file, right? And sometimes, how many of you use printf? Printf, scanf, or anything that requires standard io.h, standard library.h. So we all use that, right? We all use that. These are libraries. These are pre-implemented program. Is a code that is already been pre-built so that if you want to print something on a monitor or you want to take something from the keyboard, it already know how to do it. So you can just call the function. So you would combine this thing together, right? You basically combine this thing together and link them so that you have the executable, right? You have the executable that you can run to see how many steps that actually happen under the hood, right? So that you can start from a C file and you ended up with one single executable. And let me ask you one more question. For those of you who use Windows, anyone seen this thing called DLL? Anyone notice this type of file that's called DLL? So DLL, actually, if you look it up, it stands for Dynamically Linked Library. Dynamically Linked Library. The word dynamic has a hidden connotation. Let's say you run some program and the DLL file that the program needs is missing. What will happen? So you run certain program and have you run into an instance of your program crashing and say, hey, I cannot find this DLL file? Does it ever happen to you? So it does happen to me. It does happen to you. Okay, thank you for the response. Yes, it actually does happen, right? The reason why this happened is because these type of file, instead of this linking process being done before you produce the executable file, this dynamically linked library link afterward when you run the program. This is happen when you run the program. So the key here is your executable doesn't really contain this code for the library. It just know that when I run and when I hit this line, I'll call this function. This function should be available on your computer somehow, right? And you can run those functions. So this is how the executable work with the other kind of like the pre-built library on your computer so that you can have fancy program running, right? Things like WebEx, PowerPoint, and all the really nice software that you've been using so far has similar process, right? When you want to create executable file. So now I talk about this library, right? Let me kind of dig deeper into the concepts. It's still high level, but I want to give you the conceptual part that allow you to keep digging deeper after the semester is over if you want to, right? So what a library? So actually, what I'm not going to talk about our like your generation for sure. Let me talk about my parents or your parents' generation. What do they use the library for? Like, don't ask me what I use the library for. When I was at CMU, the only thing I used in the library is go there and take a nap between classes. That's the only use of the library, right? You can go there and reading, right? Would you go there to the reading? Because there's a lot of reference book, right? You can read a bunch of books that someone put there, right? So that's kind of like a purpose of a library, I guess, at least back in the day. These days, like kind of study building, you can kind of have a group study. You can do what I did, take a nap over there, after going like until 3 a.m. trying to finish the assignments. So these are why we also call this pre-implemented code a library, right? Why is that? We all used this thing before, right? Standard io.h, standard library.h, and math.h. Everything here is pre-built, right? Everything here provides the program with a reference of how do I do all this task, right? How do I do all this task? And from the earlier, right, from the earlier figure, you saw two different kind of instance, right, of uh how library can be invoked. You can have a static library, right? Static in computer science. Static mean, as the name suggests, it's kind of like permanent, static, constant kind of thing, right? So basically, these happen. The usage of the library would happen when you link them together in compile time. There's a notion in computer science, there's a notion between compile time versus runtime. Anyone want to guess the difference between compile time and runtime? If I said this happened during the compile time, what does it mean? Versus this happened at runtime. Exactly, right? When I said this happened during the compile time, it literally means that this particular process is done when you compile the program. So afterward it's now pre-built into the executable. If I say this task happened at runtime, this task happened at runtime, it means that whatever you're trying to do here will trigger when you run it. When you run it. So static library would combine, right? Basically would combine your C object code, right? Basically your code along with the library file when you compile. When you compile, that would generate the executable when you compile the program. This is in contrast with the dynamic library. Dynamic library, as the name suggests, instead of running and linking at the compile time, the actual link mean I can now refer to what I want to do, right? Because library is like a reference function that I can run. I would then link at the time I'm running. This basically means that the link operation performed right when the executable is run, when you run the program. So with this, you need to make sure that the library is still there in the path that you specify, right? In the path that you specify. Otherwise, your program cannot find the library. It's like when you want to walk to the library, whenever you want to need, whenever you need to use the library, and now the library is gone, you don't know how to get there. So you want to make sure the location of the library file is loaded in certain environment variable. In Windows, it's a different name, but in Unix, it's LD library path. This is where you store the path for the library file, right? So this allows you to run your program and utilize this pre-built library. And that's also a trade-off, right? That comes with, should I use static library, or sometimes some certain programs, some certain library is better to be used dynamically. this kind of depends on your demand, your application, right? This depends on your application and how you want to use it. Because at the end of the day, right? At the end of the day, you are the programmer. To the computer, you are the god. You tell them what to do, right? So these are tools that's available to you that you can use. You can do a certain thing and use a static library, or you can use a dynamic library. If you want to make sure the library is aware of the state of the computer, the dynamic library might be better because this happened at runtime. So the library can measure the state of your computer. Are there multiple program running, things like that, right? If you don't care about that, you just want to package them into an executable, static library is perfect for that. You can now compile and you don't have to do it again, right? It's there with the executable. There's another library that is called the shared library. So if you use Linux, for example, you might run across this file called the .so file. The file that end with the .so. These are static objects. These are static library where multiple programs can use this one library. So each program can use the library and lead to the share the loading of the shared library is typically done at runtime because they're actually being shared amongst many processes. All right. And there's also you can update your library as well, right? So if you statically compile and use a static library, if you want to upgrade, what do you do? So if you have a static library and you want to update the static library into your executable, you need to recompile, right? You need to compile it again because right now your executable has the old version. The only way you can do this is to recompile. If you happen to use dynamic library, the dynamic library doesn't really get linked until you run. So you can just update the dynamic library and then you run the same program again. It would work. And it would work with the new library, basically, as long as it have this backward compatibility support, right? So that's kind of like the gist of how this linking process works. And before we kind of wrap up with the compilation process, there's one last thing I want to talk about, which is optimization flag. This is handy for you to know because GCC can optimize your code automatically as well, right? This is good because instead of using a default one, which is -O0, this is dash lowercase o and number 0. GCC actually comes with multiple level of optimization. It actually has multiple level of optimization. Let me pull it up here, right? Uh, these are the optimization option that you can use, right? Can you see my screen? So if you read this is basically the manual from GCC GNU.org. Basically, this is like a default GCC that we all use, right? And there's a section for the explanation of the cool things that GCC can do. So you can add, for example, dash. Where's my mouse? Where is my mouse? I cannot find my mouse so that I can scroll down. Okay, here. So you can do -O1, for example. -O1, it would basically turns on. So with this, like the documentation say, if I do -O1 when you compile, it basically enabling this techniques. Everything here, right? Everything here. These are techniques that are being done, prove most of the time, prove that it's correct being researched on, right? Some of these actually come from a paper, like someone discovered, hey, you can do this to optimize your code, and you can apply these techniques and make your code run faster. They published the paper. Someone take that findings, integrate that to GCC, and now you have this functionality that you can do. So O1 would do all this optimization. If you want to go one step further, dash O2 would perform everything in O1 plus here many other things here that are called different. Basically, these are techniques that would apply. In the slides, I will talk about this one particular technique called F inline small function. It has to do with making function call much faster. But you can see there's multiple things that are being applied. Some of them would be done for the loop. Some of them are optimization done for if else. Some of them are optimization that are being done for constant and how to propagate constant so your program run faster. How to optimize for a string length right over here, right? And if you want to go all the way to O3, O3 is basically everything O2, including this, right? Including these techniques. You can kind of like dig deeper into this document. Right? The document would tell you what each of the particular optimization do to your program, So I'm gonna bring it back to my slides, right? Uh, here. So one thing you can do is to try to play around with this. One encouragement that I really want you to try is when you have a big C program, try to do dash O3 and see if that's faster. Especially if your program has to touch multiple pieces of data. When your program is complicated, try dash O3 and see if that's faster or not. I can tell you one of the joke. In CMU, there's one class called How to Write Fast Code, right? And when I was a graduate student, one of my friends in the group, in the research group, actually did take the class, and he was joking that one of the things he did, and you get a really good speed up, but your code are really fast afterward is I just added dash O3 to compilation process, and now my assignments get a lot faster, right? So joking as I mean, this is something you can do, right? These are something that has been proven by the great people who do compiler research as well as programming language research into making sure these are possible and is still hopefully bug free. So feel free to use it. You can use also dash or G, the letter G, to optimize debugging experience. If you want more information, these are available at basically that online documentation from gcc.gnu.org. It contains all these information. And based on what we saw so far, right, I'm going to talk about one key techniques that actually it's been invented a long time ago and we use it still now, right, to make your code faster. It's called inlining. So from our from our assembly part 3, what did we learn about function call? When you call a function, we need to create the stack, right? And we need to allocate new variable local to that function call, right? So this thing, where is your stack? Where's the stack located on your computer? Where can I locate the stack? When you buy a machine, install Windows or Linux, where's the stack? It's in the memory, right? And from our caching lecture, what did we learn about memory? What did we learn about memory when we are going through the caching lecture? So the good thing about the memories is big. But the bad thing about the memories is actually slow, right? It's slow, but big, right? So whenever you have operation that has to do with the stack, these are going to take some time compared to just adding, multiplying. Those will be a lot faster, right? So the technique called inline function, basically what it does is when you have a code like this, like I say, you have a function called int add int a int B, right? And then you return A plus B, something like this really short function, right? And then in other function, like a main function, you have add, like C equals add A and B, right? What would happen here? You call another function, right? You create a stack, allocate new variable for A and B, you add them together, return, get rid of the stack part that you just created. Inline function would replace this with the function body, right? So this gets replaced with C equals A plus B. Inlining. And you can literally, you can do this optimization by turn on the optimization flag, or you can declare this inline. If you add the word inline in your code, the compiler would literally put this inside the function that called this function. This is one of the techniques that actually get used really often, right? So there are many things that are similar to this. There are many things in compiler that are trying to do something similar to this. Many like, for example, let's say you have C equals 0 somewhere, and then way later you have A equals C plus 1. What's the value of A? Can someone tell me what's the value of A in this case? It's 1, right? So actually, there's a technique called constant propagation. Constant propagation, as the name suggests, it would actually search your code and look for these things. Instead of having to do, hey, what's the value of C? Let me add 1 to that, and I write that to A. I'll get rid of this. You have A equals 1. Compiler actually do this for you. That's actually many cool tricks that are being done in compiler that leads to performance improvement, right? So these are little things that you can enable with the optimization flag. So I again, back to the key message, try it out. It's good. It's as simple as try it out. It's good. Any questions before we talk about the Makefile? So now let's talk about the Makefile, right? Now that we know cool tricks that we can do with the compiler, what is a Makefile? So you've used the Makefile before, especially for assignment 3, right? If you somehow look into what is inside the Makefile, it's a list of directions on how I can build my program. I have a lot of .c file. The Makefile would dictate how do I create executable, something I can run. You can declare the requirements. These are called prerequisites. And then you can put in the set of command to each of the target. Target is basically the outcome of the compilation, right? It's a file that's going to be created after you run the command. So the format of the Makefile would contain something that looks similar to this. Target name, it would have target name, colon, prerequisite. Prerequisite, typically these are the file name. These are going to be the file name. What Makefile would do, it would first search if you have the file. If the file exists, it would run command 1, followed by command 2, followed by command 3, followed by command 4, 5, 6, 7 to command n that are given by the target. So think of this as a program. It's a program that helps you install your, or not install, but build your executable, right? I mean, on a Windows term, I think it's behave almost like an installer to some extent, right? This is how you can build your software. So now your question might be like, okay, I know there's a bunch of command you can do. So what can go in there? Basically any shell command. Shell command can go into the command of the Makefile, making this would look almost similar like a bash script, right? That you learn from the first module of this semester, because variables, surprise, also go with the same format. The $sign would specify the variable. It works the same way as the Linux bash script, right? You can also create a target with a phony target. Something like, let's say I want to create a Makefile, and then I want to have the cleanup code for assignment 3. You can do make clean, for example, right? Make clean. Make clean would basically remove executable file, and you ended up with just C file by determining what you are supposed to do with the clean process, right? To prevent creating a new file, you can use phony. For example, you can do phony : clean, and then when you clean when you actually run make clean, the Makefile basically go here and run rm-rf star.o, which is basically I'm gonna get rid of any .o file from here, right? And you see the star here, right? It's a wildcard. So Makefile also work with wildcard. For example, you have 1,000 different .c file. You don't want to type them all, right? You don't want to type them all. So one thing that you can do is to compile using star.c. You can compile using star.c. This would basically would allow you to apply. It would apply the command of whatever you list, right? Because you have a target and then the prerequisite, right? And then you have the command right here. It would basically apply these commands to every single .c file that occurs there. And now that you have a target, you can have multiple targets as well. You can have multiple targets. So for example, you can have a target called test1 and another target called test2, right? In this case, when you type in make test1, it would do whatever is specified by test1. You can do make test2 would specify, it would run whatever is specified in test2. If you type in make all is another special target where you would group multiple targets together. In this case, when you type in make all, it will actually first do target 1, followed by target 2, followed by target 3. It would do all the tasks that you list there. So one more common command that you are going to give is make clean all. Make clean all would first clean the current build, get rid of the executable, followed by I'm gonna rebuild whatever executable I have. Let's say you have the code updates and things like that, right? About code updates, one thing nice about the Makefile is it can also detect if you have updates in the code. If there is, when you type in make, it would rerun the compilation process so that you can generate a new executable. If it's the same old file, it will say, hey, there's nothing to be done because you already have the most updated version of the file, right? You can also specify the compiler using CC. That would basically allow you to specify the C compiler. In this case, I can say cc equal gcc. It means I'm going to use the gcc command to compile my .c file. If I want specific version of the GCC, I can do cc equal gcc-4.4. In this case, it would actually use the GCC version 4.4 to compile your file. If you want to use the C++ compiler, that's CXX, and you can do the same thing here. You specify the compiler that you want to use. It can be a specific version of G++. G++ is the compiler name. Think GCC, but for the C++ language. Or you can use CLang, for example. CLang is used in, say, MacBook, actually use CLang to compile both C and C++ file. You can also specify the arguments like -03 or -g, right? -g would allow you to actually use GDB. So you can do C flag. C flag would get added to the C compiler process. So if you use GCC, it would add whatever you put in the C flag as an argument. CXX flag applies to C++. right? And then the LD flag is if you want to load any linker, for example, if you use certain libraries, then you can do the LD flags. It would actually load those libraries into the compilation process as well. You can also use if else, like if not equal and if equal, right? This is handy in case you need to make certain things like you want to check the username of someone who run the make file. If it's this user, go make the file in this particular directory. Otherwise, use another different directory. You can also, let's say you download multiple programs together, right? It comes with its own make file. You can then export the variable inside one of the make file to another make file. You can call another make file that are in a parent make file. For example, let's say I download multiple programs and I want to build all of them. But I want to build all of them in a way that they work with each other. So each program has its own make file. There's going to be one thing I can do is write another parent makefile that would go and call each of these individual makefile. You go in cd into that directory, make, basically call that particular makefile, cd dot dot slash, go back to the parent directory, and then cd into another directory to make that. You can make a parent makefile that would be like basically becoming this coordinator into building all the software inside these giant projects as well. So it's really powerful. I have a slide called question, but basically that's the end of the lecture part to actually show you the example of the makefile. I'm gonna first stop sharing here, and I'm gonna share you the makefile for assignment 3 on my desktop. All right, so let me bring up the PuTTY so I can connect to the server real quick. All right, so please let me know when you see the screen. I'm sharing right now the screen. In the meantime, I'm gonna change the font size so it's easier for you to see. All right, can you see my screen? Hopefully bigger now. All right, thanks for the thumbs up. Now that you see this, right? This is your old friend, the assignment 3. Right? So if you look at this, I have multiple files already built, right? I can run btest, which right now would fail everything because I haven't implemented anything. It would fail, right? For sure. If I want to clean this up, I want to get rid of all this executable file, I can run make clean, right? If I do make clean, what you see is my btest file is gone. Why is that the case? If you look into the make file, right? If you look into the make file, you can break it down by doing this. What I just did was make clean. It will go do the target clean. Inside the target clean, what I did, rm-f star.o, anything that has the .o file in here, I'm going to remove that. btest, I'm going to remove btest, fshow, and ishow, and then this particular additional any file that are not related to the .c file. Sometimes you can have file that end with like this tilde sign. So it's kind of like a temp file. You can get rid of that as well. Then if I type in make, for example, if I type in make, you'll see that what is happening is I built this binary back, right? So let's go back to the make file to do this, like breaking down what happened. The first line basically specify there's a variable called cc. I would use gcc as a compiler. For the compiler, I'm going to add the dash o, dash o, this is a capital letter O, dash WR, and dash M32. The dash M32 is the magic trick here we put in for this particular exercise. Why is that the case? This assignment need to use 32-bit architecture. It forces you to use the 32-bit architecture with the dash M32. Then it would use the library called LM, right? And then when you type in make, it would go to the first target here, which is make all. Make all would then do the target B test, followed by the target F show, followed by the target I show. So what is in B test? B test asks for btest.c, bits.c, decl.c, test.c, btest.h, and bit.h. If these files are not in this directory, it would yell at you saying, hey, I'm missing this target because the prerequisite is gone. You need to make sure you have all these prerequisites. If it successfully checked this condition, it is going to then run this command. What is the command here? $CC, that's GCC, right? $C flag, that's dash O dash WR dash M32. $libs, that's dash LM. And then you add dash O B test, which is basically the output, right? You're gonna output B test as an executable and use this C file as an input. Then I'm gonna do fshow. We'll check if the file called fshow.c exists. Use GCC with the flags for the fshow and the ishow executable. Right. So that's why when I type in make, I now built out this tester, right? The test as well as fshow and ishow. All right. So that's it for the example. Any questions before we now move on to Discord? I want to make sure I use the remainder of the time that we have on assignment 3, assignment 4. I want to make sure everyone has like the idea on the same page. If you're still stuck with assignment 3, I want to make sure you are aware or at least have a hint of how to get things done. So first I'll stop the recording.